heard his name and read all his famous work. So I'm sure you will hear some of them today. So his topic is ESM and naturalness. Go ahead.
Okay. I'm presuming the mic is working. Anyway, great to be here after a bit of a many-year break from the last time I was here. So just a technical thing, I have put up some notes, or rather my daughter did. She didn't do a great job, so I might have the professionals redo it. And I'll add more notes to that, so that's not the final set. I'll add more if once I get a sense of the timing and pacing. And there are some references there, and again, that'll be updated, and then hopefully I'll add some exercises as well. Good. So the lectures will have some beautiful equations. Not too many in that sense, but I hope that they are useful and not easy to distill from the infinite literature. But they're really, those are the skeleton to what I'm mostly presenting, which is some sort of perspective, and the perspective is mine. It's not, I'm not able to teach you an objective, this is what's beyond the standard model, because I don't fully know, as you know perfectly well. No theorist knows exactly what lies beyond the standard model. So it's my perspective on how to even think about it, how to even intuit what it might be, what considerations should come in. And so there is some humility in presenting it. And I would just ask that you take it in and toss it around yourselves, talk among yourselves, and come to your own perspective, because there is no actual leader of the field in that sense when you go beyond the standard model, okay? So to start, where do I start that? In fact, this little section, I should say, has a name, at least when I was talking to myself, which is, yes, there are some equations, but I wanted to start with some metaphors, which you may be impatient with, but I feel they get you into the mood of what I am trying to do. And so to start, to me, if you just look at what we already know pretty well, the standard model and general relativity, these are really exquisitely beautiful, okay, as theories, and integrated together, it is just an exquisitely beautiful, effective theory. And I feel it's worth reminding yourselves of that beauty, because that's one of the things that you're saying, look, if anything's going to top this, then it should have that flavor to it, right? It should move your emotions as much as just your brain. And so I was looking to see, is there a poem to the standard model which just puts you in the right mindset? And to me, there has always been just one that I'm aware of. And that is sort of this, I've called it reference one here in the list. But basically, it's Howard Georgi's rather short book on weak interactions in particle physics, which is on his website. And it does both what is the standard model, its experimental underpinnings, and the methodology of a theorist in understanding it. And because it's short, in my view, it reads like a poem. It has an attitude rather than, here's the encyclopedia, standard modelica, or whatever. So it's worth taking a look at just to get into the spirit of, wow, this is just like, if I just stopped here and left the field, I would already have riches beyond compare, okay? Good, so in some sense, the metaphor I have is that you're hearing beautiful music, just look around you, and there seems to be in the distance an orchestra playing. And in the distance, you can see at least part of the orchestra, and that is the standard model in general relativity. But there's more sound that's playing out there, and you're missing something, and we want to figure out what that is, right? But this orchestra that we can see is already well integrated. The score and everything has combined all the instruments in this beautiful, harmonious whole, okay? It's worth getting the sense for that, because that is already experimentally tested. So I'm trying to ask the question, when we go beyond the standard model, I'm doing it in a particular direction, in these finite lectures, which is how to go beyond the standard model in a comprehensive, panoramic way. Okay, not just one little glitch or one little experimental anomaly, which I think is great stuff, but something based on deep quantum field theory mechanisms worthy of the standard model itself. Of course, it has to respect the data that we have, of course, but it should also respect the standard model in the sense that if the standard model gives a beautiful explanation of something, the best clue is that's not a coincidence that has to be thrown out when you go beyond the standard model, but rather something integrated into whatever goes beyond the standard model. So in a way, because I'm not actually an expert on what lies beyond the standard model, I don't actually know, I wanted to give you something like those ancient maps that you may have seen at some time or another, where, like, if you looked at like an ancient map drawn by the ancient Greeks, right? They would have some exquisite detail. I don't even know what Greece looks like, right? But they would have exquisite detail of Greece. And then there would be some very distorted picture, you know, of Africa or whatever, and Europe, and there would be a very distorted sense of nothingness and just little bits and pieces, and we wouldn't know very much. And that's what I'd like to give you, because I think these are not like a modern map, right? This is not like Google Maps, but it's an explorer's map, right? It means there's something left to do. There's a world to explore, and I want you to at least have the map that I have to go exploring yourself, okay? And then you want to update the map, and you want to consider alternate maps as you and your friends keep discussing what the hell is going on, okay? In terms of, you know, what I consider a kind of panoramic vision of BSM or a panoramic or comprehensive motive, you know, it's very much like here's the flat Earth, which is the standard model in general relativity. Not that that's such a bad thing. Even a flat Earth is a gigantic conception, okay? But we're looking, when we go beyond the standard model, for, you know, some major new principle, some new paradigm beyond the details, something big picture, and we're trying to understand how this fits in, you know, that this is, say, experiment up till now, but it charts a course for exploration to try and see. And it seems to me that if whichever BSM direction we go, which gives a grand new vista like this of a possibility, it's possible that experiments will be directed as to looking for the roundness, right, that goes beyond the standard model, the big theme, the big new theme. It's possible that experiments in our lifetime just may not have the span to truly see the new theme. It's even possible that the new theme is wrong, okay? But I'm making a plea to say that even putting forward the new theme in a clear way is worthwhile, okay? In some way, it's worthwhile in directing experiments and thinking about alternates. It's worthwhile. And so we should go for these grand, ambitious new themes beyond the standard model. So I'll end that little section by just saying, I think it's okay. I'm only saying this because I get a counter saying from the current culture, which is, I think it's okay to play with alternate universes in your mind. We're theorists. We're not experimentalists. We have luxuries that they don't have. It's okay for us to go into alternate universes. It's okay to go where experiments can't follow. See, even, or at least not follow yet, but maybe not even follow. I'll get to you in a second. To even play with mechanisms which have no obvious purpose, okay? Before quickly snapping back to reality and talking about practical experiments that we can do on a tabletop or in outer space and so on, which is all great stuff. But I think it's worth being able to spend time in this way. And let me just say that there's a set of people like me who live in that spirit in the field, and we feel a little bit antiquated. And I think affectionately to ourselves, we sort of call ourselves the Jedi in Star Wars terms, in the sense that the rest of the world thinks that's worthless. That's worthless. It's what's the point? And it's so silly, and it's so yesteryear. So unapologetically, that's the direction I'm coming at it from. And I'm hoping that with whatever I can give you, that you can face, the visible forces and the forces of darkness and all of that. Okay? Question.
I don't agree with you. I'm just curious. Why do you think beyond the standard model theory should be as beautiful or elegant as the standard model?
No, I don't think it has to be. I don't think it has to be. But and in very small ways, it may not be. Even the standard model itself, in certain steps, the step was just like, oh gosh, here's a 2x2 matrix diagonal. It was just some dumb thing. Like, I didn't spend 6 years in grad school just to do a 2x2, but it was the 2x2 matrix that somehow propelled the field. So I don't think, at the time, it may not even look like that. So I don't say that only thinking grand thoughts will lead you to grandeur, right? It actually might be that tiny little hole that leads you to something truly grand. So again, in some sense, I'm only saying this to counter the other part, that's sort of the way that the field sort of has in its mind. Not to negate that. I just want both. At lunchtime, it's worth talking about grand ideas like supersymmetry, and at other times, it's like, okay, here's this mixing of the dark photon and the light photon, and it's a little matrix. And it's all good. I'd rather have both. I'm just saying I personally enjoy both aspects. And there is a part, the standard model itself, which you can already enjoy. And you cannot say was a small thing, right? There may be occasions where something big falls into your lap. It's happened before. It surely remains to happen again, okay? Okay, so on a kind of grim note, I want to talk about the end of particle physics. Just to begin the lecture. Okay. And in a certain multiple meaning sense, the ends of particle physics. But now I'm starting in earnest. Okay, so it's really just where shall I do this? I guess it's just starting with this concept of the Planck scale, however you define it, somewhere around this scale, right? And it's worth just again tasting the flavor of it. Of course, everybody knows how to get that scale, but it's worth again just knowing the meaning of it. That if there was an elementary particle, it is the end of particle physics in that we have particles down here, but a particle up here, a particle with a mass up there, would have its Compton wavelength 1 over m would be bigger than its classical Schwarzschild radius, which is g Newton m. Sorry, the other way around. Okay? And in that sense, it would not be a truly quantum particle. It would be more just a classical black hole. Okay? So particle physics above the scale, in that sense, doesn't make sense. And then there's just the related meaning that particle physics we think of as a way of focusing to get a microscope on shorter distances. And so if we attempt to probe distances smaller than the Planck length, then to do that would require an energy which is bigger than m Planck, again. Okay, and again, that means we start producing large black holes. Okay, So there's an obstruction to going to shorter distances than the Planck length, and there's an obstruction to trying to think about particle physics as particle physics above this scale. It's a wonderful world up here, but it's not particle physics, okay? So that's one end of particle physics. You can build a bigger and bigger collider, but at some point, the flavor of how you do particle physics and go to shorter distances breaks down when you get to this scale, at least, I mean, at the latest by this scale. Okay, so that means that somehow, of course, it's also, you get m Planck out of g Newton by using h bar and c. And so this is really the scale, the maximal scale at which a theory of quantum gravity, a full theory of quantum gravity, has to sort of come in, okay? But that means that below this scale, we are in the land of particle physics, and from a theoretical perspective, we must match on at some point below the scale, maybe not too far below the scale, we have to match on to a quantum, not field theory, but effective field theory below the Planck scale, okay? And somehow, the universe that we see at lower energies unfolds, you can sort of say it in a formal way, as we renormalization group evolve to low energy. This effective field theory unpacks itself, and all the scales that we associate with experiments somehow emerge, okay? And so we'd like to understand that, okay? And I should say that effective field theory, therefore, becomes one of the most important tools. And have you already had your effective field theory lectures? Yeah, okay. So, one course of lectures is not enough, but you've been grad students, and it's been coming up no matter what you've been working on. But understanding it in some as deep a way as you can is worthwhile when you're trying to take this expansive view of going beyond the standard model. So, of course, what do we see? What's worth understanding here? We seem to have evidence, circumstantial evidence at least, that somewhere not too far from the Planck scale in a very log sense, okay, there's something like grand unification. So, we already know there's a famous thing which is that if I plot 1 over the coupling constants roughly, and the renormalization group scale, with just the standard model running, and starting at MZ, say where we take the data, starting from the experimental values of the QCD coupling and the SU2 electroweak coupling and the hypercharge coupling, that we get something that looks vaguely like this. And as if, so if this is clearly not intersecting, but if it had intersected, or if this is just if there's some other subtlety going on than just the standard model renormalization group, this is exactly what you'd expect for some form of grand unification. For example, some sort of a Higgs mechanism where SU5 or some grand unified theory breaks down to SU3 cross SU2 cross U1. And at the scale of Higgsing, before it's Higgsed, SU5 has only a single coupling, and then these couplings diverge in the standard model as you go to, with standard model running, down to low energy scales where they look very different at experimental energies. So there's a whole story of this. This is not where I'm going to plant the flag of BSM, because I think it's easy enough for you to read a review and get the spirit of it, or read a textbook and get the spirit of it. For example, it's reviewed in the particle data group reviews, which cover many topics in phenomenology, including grand unification in all its different guises. So I think it's worth seeing, even if it's not what you do on a daily basis. It's worth seeing that something seems to be up. The quantum numbers of all the standard model representations seem to be fitting into some sort of a grand unified representation, at least as far as the fermions are concerned. So there's some evidence like that. So there's something like a gut scale. For those who play with neutrino masses, if you are, if in at least the seesaw mechanism seems to at least point to, again, you have to read into it, but seems to point to high energies. Of course, the LHC operates at much lower energies than that. And we see all sorts of things with the LHC and prior colliders, like the top and the Higgs, and here's the B, and here's the mu and the electron. Okay, and keep going. There's literally the size of the universe, or the age of the universe. I'm doing what I was told not to do, which is writing small. Okay, but okay. Good. So we see a hugely hierarchical world, even experimentally with a little bit of reading into it, but they seem to be pointing to scales which are incredibly hierarchical. And so one question is, what robust and economical mechanisms underlie these hierarchies. Hierarchies, okay. So this is a partial answer to the question you asked, which is the way to progress to try and be panoramic and comprehensive in one's thinking? No, I don't know. I don't know. But this is at least such a striking thing that, just out of natural curiosity, you are led to look at this and wonder, how did that unfold? What was in the DNA of this quantum gravity theory that, as you kept evolving it and so on, just sort of spat out all of these different scales? And I'm not doing it justice, but all of the subtlety of this. Is there such a thing? It's just an interesting question. Okay, so I don't want to oversell it and say that I know that this is the path to Nobel Prizes. It may or may not be, but it's what grabs me. Okay, so I want to give an example of something which even tries to be in the spirit of this question, which we already know is true. Okay, and I'm just reminding you, I think you all know that, and that's the idea of exponential hierarchies. I hate this particular, I'm not fast enough. Exponential hierarchies. From nonperturbative physics. So one of the things I'm selling, to the extent that I'm trying to convince you of anything, it just strikes me as very likely, is that non-perturbative physics, we all spend a lot of time with perturbative physics, and rightfully so. It's such a powerful tool, and a lot of the world subscribes to it, and maybe BSM does too. But I think we will see nonperturbative physics is very likely to play a pivotal role in the kind of reasons behind that kind of hierarchy. And the simplest example of that is the proton mass, which in the limit, just to make it simple to discuss, in the limit in which m quark in the Lagrangian, the parameter, the quark mass parameter is 0 for simplicity, which is approximately true for the up and down quarks. Okay, and formally, well, let me just say it like this. What is this mass, right? We know that from renormalization group invariance, since when there's no quark mass in the Lagrangian, it has to emerge in some way from a theory which has a dimensionless coupling. It has a dimensionless coupling alpha QCD, which is running. And so the only thing that this proton mass could be is this famous formula. This alpha naught, sorry, this x naught is some integration constant, but okay. Out of the parameters mu and alpha of mu, this is the only renormalization group invariant scale that can be made. Okay, and where this is the beta function of alpha. And if you've never seen this before, then just check that this is actually renormalization group invariant, meaning that if you do dd log mu of this, you get 0. Okay. So there it is. In one shot, you're told a very specific form. And this is roughly, depending on exactly what this integration constant x naught is, it's either the proton mass or it's basically what we call lambda QCD in the most fundamental sense. Okay? It is the renormalization group invariant of massless QCD. So we can always, just to test it out, we can evaluate this at the renormalization scale m Planck. And to good approximation, we can use energies roughly of order m Planck. If we're just trying to do a sloppy job, we can just use the one loop approximation where the beta function is basically one loop in form, alpha squared times a constant. And then this is approximately some constant, which depends on whatever x naught is. But I'm really looking at the parametric dependence on alpha. Okay. That the proton mass, first of all, is given by a formula where the coupling that emerges from quantum gravity at the Planck scale, alpha renormalized at m Planck, if it's just a little bit small, this b, I don't care, it's order 1. So if this alpha is a little bit small, then the proton mass becomes exponentially small relative to the Planck scale. Okay? So it even gives meaning to the question when you say, what underlies these hierarchies? What does it even mean to ask that? Why don't you just put the hierarchies in by hand? Then that'll account for it. So here, we're trying to read what we're seeing in the data. And here is something very powerful that we actually know is true, that the proton mass is vastly smaller than the Planck scale because the the QCD coupling at the Planck scale is just a little bit small. Okay, this hierarchy has been stretched out for a modestly small alpha into an incredibly small proton mass. Okay, and you can see it is non-perturbative. Right? It's e to the minus 1 over alpha, which, if you do a Taylor expansion for small alpha, is 0 at every order in perturbation theory, but non-zero in truth. Okay, okay, this is dimensional transmutation. Everybody has heard of it, I hope, and you've seen it before. But I'm just asking you to feel into it now and just say, "Oh, this is good. This is good." I wish there was a story of BSM where everything was of this type, like where all the hierarchies just sort of came out of things that are as striking as this. And what I want to do in these very short lectures is give you the fast track to that. I want to give you a theory which is essentially complete in the sense that it's an effective field theory below the Planck scale. Planck scale, yeah. And which lives up to the spirit of this statement, that all the hierarchies that we normally agonize over and so on just unfold from this kind of mechanism that's in the spirit of this mechanism. And it'll use things that you've heard of seen before, but I don't think you'll have seen it all put together in as concise a way as this, okay? It's a funny thing that I participated in some of this, other people participated in a lot of the development of these, so this is the work of many, many people. What I was noticing the other day is that as we were doing this work of writing down mechanisms, we were like you, we were just like, I want to write a paper. So we were writing papers and so on. And nobody ever stood back and said, so what has been accomplished? Like, where are we at the end? And so it hasn't been written down like that as a sort of like, we can at least do this much. It may not be true. The Earth may not be round, but it's something. It's something to consider. Okay, so I want to talk about. I want to switch to a technical aspect that, again, you sort of know. I call it spinning tails, which is pretty much what I've been doing up till now. But here I mean it in a technical sense. Where we will see another end of particle physics. By the way, there's, of course, the ends of particle physics, meaning what are its goals. And for these lectures, you can have many ends. There are many different lectures in the series of TASI and so on. But for me, that's it. Okay, I'm saying it. But here, we know that the energy of experiments in the standard collider sense and so on are vastly smaller than the Planck scale. And given E equals mc squared, that means that the masses that we experimentally detect are vastly smaller than the Planck scale. So, okay, at least directly do it. So that means on the biggest stage, and you see the whole lecture is taking the big stage as the stage. That means that the masses are approximately zero and are likely to stay approximately zero in this sense, even at the next collider or whatever, okay? So we should ask, what do we know about, from a field theory basis, what do we know about small masses? Really, from the point of view of relativity and quantum mechanics, what can we say about small masses? Because one way to talk about all of these is to simply take off my glasses, I can do it, and all of them look like this. That's it, right? Okay. So I want to ask, that's a strange thing. Here's a theory which is sort of fundamentally all about something emerging out of quantum gravity, and yet, what robustly allows all these particles to be massless? In fact, is that even a question? Why didn't I just put m equals 0 in the Lagrangian? What allows that to happen? Okay. Well, and 1 second. And what would make that even to answer that question, you first have to answer it. It's ill-defined. You have to answer it and taste the answer. Okay. Yeah.
So thinking in kind of this large way, isn't there a huge philosophical difference between zero mass and finite small mass?
It may or may not be true, right? And technically there are, and we'll have examples of that. But taste what I'm saying and then get back to me. Okay? So I feel that partly the bad press that the Jedi have got is because in the past they have oversold and have tried to schematize whatever it is that's in their hearts. And that doesn't work. Nobody has that way of viewing reality at this point. So I want to back off from that. And so often the answers to questions like this will be, well, let me give you the answer to a very ill-defined question, maybe even philosophically unsound. But the answer is very concrete in a certain sense. And let's just taste it and go, I get it. Now, what would be next that tastes similar, right? How would I finish the symphony? Okay. Okay, so I'm starting it just as a function of spins, okay? J equals 0, etc. Okay. So spin 0. What do we know? Well, that's sort of robust. Of course, you all know the answer, that you should have like Nambu-Goldstone bosons have a robust reason for why m equals 0. Let's just take what we know. You might say, what if there's a really tricky thing I haven't heard of? Great, go write that paper. But let's just put together quickly what we know, okay? How does it work? Basically, if you have a, so it's all about symmetries, okay? And so I should say, the theme of this is it's going to be all about symmetries that you might call protective symmetries. They protect this special place, m equals 0, and even m close to 0, okay? So the symmetries here are, there's some continuous symmetry. You know Goldstones Theorem. So there's some symmetry current, the Noether current of some global symmetry. And of course, I'm not giving you a field theory course. I'm just reminding you that, roughly speaking, what does this current look like when there is spontaneous symmetry breaking, when you get Nambu-Goldstone bosons? It looks like the derivative of the Goldstone boson plus terms which are nonlinear in the fields, in whatever fields there are. Even nonlinear in phi, perhaps. Okay? So that's the quick thing. And so the key thing, the key step in the Goldstone theorem then becomes that current conservation, right? That the symmetry implies current conservation. That's Noether's theorem. And you can see here that this is equal to plus nonlinear terms. But to read the mass of phi, I don't need these nonlinear terms. The mass of phi is 0. Okay, so that's Goldstone's theorem. I'm not. This is not a substitute for a field theory course. I'm just summarizing what you know. Okay, and of course, if there's, maybe I should do it here. If there's a small, so coming to your question of not being quite 0, we play around with it here. We say that small explicit, this is spontaneous breaking, but explicit symmetry breaking, small explicit symmetry breaking would then imply that you can get small masses. Okay, if it's small, then consequence is small. And then we would call these pseudo Goldstone bosons, or just, okay. So already we're thinking like a theorist. In a world in which we could turn off that explicit symmetry breaking, they would be Goldstone bosons. So we continue to call them Goldstone bosons in some form, namely pseudo-Goldstone bosons. And a final thing, maybe I'll keep it here, is that under the symmetry, phi, under the symmetry transformation, has famously, for internal symmetries, has a shift form. So constant, and then there may be higher order corrections. But the fact that you have a shift symmetry for the Goldstone boson says that, maybe I'll do it here, says that the other critical thing the other critical thing is that that means that invariant couplings contain the derivative of phi, because then it is invariant under this symmetry. Okay, so we tend to have couplings that are derivative in form, and that turns out to mean that that phi is very weakly coupled and can be very weakly coupled at very low energies. Okay, so the lower we go in energy, the more weakly coupled it is. Yeah.
How does the derivative tell us this? Or like, how did you? Where does this last statement come from?
Yeah. So just to say that, suppose I had a potential for phi. That's not derivative coupling. Then under some sort of shift like this would go to v of phi plus constant, and that's not for any non-trivial v. That's not invariant, right? Whereas if I write something like d mu phi, and then I write something else made out of some other fields, that is invariant. Okay. So again, these are sort of the standard backdrop of Goldstone bosons. But we see that there's a price for being light. In other words, maybe there are lots of these very light guys that are even below collider energies, but they're hard to see because they're derivatively coupled, which means that depending on exactly what the coefficients are, I'm making a parametric statement, which is that if you go sufficiently low in energies, they start decoupling from everything else, and that makes them hard to see. So examples. One, famously, Axions. So every second talk and many lectures here, I hope, are devoted rightly to the physics of axions. Why? Because they're so generic, they're so robust, and experimentally, they have a little twist to them, which is they may be sitting under your feet from collider perspectives, and yet they're very weakly coupled. So you have to be ingenious to see them. So that's great, right? Two, the thing that started it off, the humble pion of QCD. Okay, and again, it takes a theoretical genius to see something here. So Nambu's observation, I think it was Nambu, of course, is that the pion mass is only a handful smaller than the proton mass, right? Other hadrons, typical hadrons. It's not that much lighter than it. But as you're struggling to just make sense of it, you leave our world a little bit and you say, well, I wonder if the pion is actually a Goldstone boson with some explicit symmetry breaking, right? So that's the theoretical perspective in it. And even though this ratio is not, it's like 7 or something, I don't know, right? Okay, but of course, once you try this ansatz that it is actually a Goldstone boson, and you guess who it is a Goldstone boson of, a huge amount of data becomes intelligible. And you can read a quick version of it in George I's book on understanding strong interactions. 3, the 125 GeV Higgs. What about that? That's a scalar, spin 0. Is it a Goldstone boson? We don't know, so I'm just going to put a big question mark there. But what a great question. You know, when Nambu asked this, what a great question that was to ask. Is the pion actually a Goldstone boson, or is it just some random factor of 7? Don't bother to explain it. Just keep walking along. Is this a Goldstone boson? What a great question. How to make sense of that? So indeed, a large part of my research was related to that. But that's not what I want to, for the shortness of these lectures, that's not what I want to talk about. So instead, in the references list, when I've updated it, I'm going to give a couple of TASI lectures that actually talk about this paradigm of the Higgs as a kind of Goldstone boson of some new dynamics akin to the way pions are Goldstone bosons of the strong interactions, or QCD, okay? So that is an open experimental question, and many of the tests of the Higgs boson and so on are partially motivated by just trying to see, can we see that to be true, right? Can we get evidence that that might be true? And we don't know yet, right? The standard model itself does not say that. Is it a kind of pseudo-Goldstone boson? What we can say, here is a fictitious particle which well might exist. It's a pretty good bet that something like this is out there. This does exist, this exists, but we don't know if it's a Goldstone boson. This is definitely a Goldstone boson after all this time. And maybe I'll just say it here. Just feel into the fact that there's nothing else. How many fermions have you got in the standard model or out that you know about? Elementary particles. How many spin 1 elementary particles do you know about? We're going to go through the entire set of spins. But I'm just saying, nature is apparently economical, but it's got lots and lots of examples of all of these spin half, spin 1 things that have symmetries associated with their masslessness. But here, we don't have any other experimental, we don't have any other experimental examples, just like nothing. And even this, you could say, well, that's just this one debatable case, but that's it, right? There's a possible reason, which is the sheer weakness of coupling, if potentially, but something's up with that. Maybe. I think something's up with that, given how many of everything else there is. In fact, I would say everything that's allowed to be abundant by field theory, by relativity and quantum mechanics, is abundant, okay? Not overly abundant in the sense that it would be boring to be a particle physicist. You'd rather be a nuclear physicist. But there's lots of examples. Okay, first I should actually look at the clock. Good, okay. Okay, let's move on. So the next thing almost needs no introduction, but J equals a half. And that's the famous case where there's chiral symmetry, okay? Where, say, psi left transforms in this way, and let's just make it simple. Psi right does not transform. Hence, it's a chiral symmetry, okay? But this chiral symmetry is always broken by any kind of mass, broken by a Lorentz invariant mass of any type. I'll just use the standard Dirac mass, m psi bar psi. If you write it in terms of the left-handed and right-handed pieces, and I'm using h dot c to just mean Hermitian conjugate, complex conjugate, whatever you want. But basically, the Lorentz invariant means that the version always means that it is transforming under chiral symmetry. It is not invariant under chiral symmetry. So therefore, exact chiral symmetry therefore implies that m equals 0, okay? So we have this beautiful understanding of why it's easy for fermions to be massless. And indeed, lots of them seem to be there, very light. You can obviously break this by a small amount. Whereas here, there's a price for being massless, namely, you're very hard to find, okay? There's no price here for an interacting fermion. Okay, so spin 1. And we're getting into this tricky thing about m equals 0 and being different from m not equal to 0. But just to remind you, m not equal to 0, you can go near the rest frame if you've got a mass for spin 1 and then everything looks like your non-relativistic picture of what spin is. So you would say that if I have a spin 1 field non-relativistically, I never took my field theory course, I would say that, oh, my field is like a spatial vector, right? That's what a non-relativistic person would say, 3 components. But if I have to relativize it, then, OK, fine, it'll go into a 4 vector. But somehow, what would I expect? This 3 vector, I would say, I want it to have, in its rest frame, I want it to sort of look like a harmonic oscillator, which is to say, in momentum space, I want it to have an equation that looks like this, which is the equation of a harmonic oscillator with spring constant m, the one that you're used to. This is just the Klein-Gordon equation for each of these 3 components. But this 4th component, the unwanted guy, I would just want that to be 0. OK? So this is what I want. But I need to get it from a relativistically covariant equation. OK? Something made out of 2 derivatives or less, et cetera, et cetera. And there's one unique way to do it, which is to form the field strength that you know from Maxwell. And this is the unique, you can play around with it yourself, local equation, covariant equation, which, if you just write these out yourself, you'll see it turns into these 2 equations. If you go into the rest frame, that is, if you go into the frame in which p equals 0. I'm not telling you to go on shell. On shell is this equation. This equation is demanding you go on shell. But just writing these equations out, p equals 0 in momentum space, that gives you these 2 things. And it's the only equation that gives you these 2 things that is local, right? Let's go this form. OK? So if you haven't seen that, this is the Proca equation, the famous Proca equation. You didn't ask for field strengths. It's just the only thing that is allowed that has this property. OK? Great. So that's the m not equals 0 case. And this is a gentle way of going to the m equals 0 limit. So obviously, we can then ask what happens when m goes to 0. But I want to add interactions. OK? So rather than write it all out again, m going to 0, there. That's gone. And interactions, well, I have to write something on the right-hand side that's nonlinear in the fields. So there's one dangling index. And this is made out of nonlinear in fields. Okay. So that's what an interacting massless theory would look like. And you can't help but notice that that is Maxwell's equations. Okay. So automatically, we find that there's gauge invariance, gauge symmetry, in that that equation there is invariant under with some x-dependent gauge transformation. And but it has another delightful property, which is that if I take d nu of it, if I put d nu here and d nu here, then here the anti-symmetry of f mu nu makes this 0, and we find that the right-hand side has to be conserved. Okay, so this unspecified right-hand side has to actually be a conserved current in this way, which means that the charge associated with that, q equals integral d cubed x j0, is conserved in the colloquial sense. Okay. Did I do the terrible thing of writing under the shadow, even though I was explicitly told not? No, I didn't. I'm good. So, before we're finished with spin 1, we can just ask about this very interesting case. And of course, whose charge is that? That's just the electric charge. If I think of the gauge field as a photon, then that J is just the electric current. But it raises this almost paradoxical question: what if the charged particles include? So these are charged particles, charges. That is their charge with respect to a mu. It's a mu's equation of motion that contains the current of which some of the particles are charged. But what if this list of charged particles includes other spin 1, massless spin 1? Okay, so what should we call them? Well, they're charged, so we can call them W plus and minus, okay? And we can ask, so we have this sort of Maxwell theory where there's a current, and the current contains the charged particles, because literally the charge, J0, is measuring electric charge. But now if you tell me that you want some of the charged particles themselves to be massless spin 1, say W plus or minus, you can ask, then how does the whole thing fit together? Because each of these particles, each of these massless spin particles, massless spin 1 particles, must have the same considerations that led to that Maxwell theory for the a mu field. And the answer is, uniquely, non-abelian gauge theory, where if you want, the W plus and minus are sort of species 1 and 2 of some non-abelian, say, SU2, and the original A becomes, say, the W3, where these WIs say, and every generalization beyond it. Okay, that the glory of non-abelian gauge theory emerges as one of the possibilities for having massless particles. Okay, and now there's this question, as you know very well, massless spin 1 has 2 helicities, massive spin 1 has 3 helicities, something discrete is going on, that limit is subtle. Nevertheless, you already know the answer, so I don't need to go through the subtlety in great detail, that small m, so J equals 1, but not so, literally the W boson. These are the W bosons up till now, which were massless, sort of the Glashow version of massless, of the W boson in the history books. But the real ones, the ones that are not massless, they're just light compared to the Planck scale or any other big scale, they're approximately massless, has to go through the full subtlety of the Higgs mechanism. Okay. So the sense in which massless and small mass are related and so on has a whole physics and legal discussion that's necessary. You're already familiar with it to whatever extent you've studied it, but it's textbook stuff, and you know it goes through the Higgs mechanism. Okay, so I won't say more about that. That's because I'm moving on to even higher spins, and so let's just go to spin 2. And by the way, at this level, you can ask, what does experiment tell us? Well, it tells us we make abundant use of gauge field theory, gauge Higgs field theory, to have light spin 1 particles, right? Lots of examples, not too many, but lots. Spin 0, not so much. Spin 1, spin half, lots. Okay. Spin 2. Again, so I'm going to say this faster because I don't want to keep spending all our time on it. But the massive case, again, a non-relativistic undergrad would say that in the rest frame, you know, spin 2 is like spin 1 cross spin 1. But you should take the symmetric. You should take the symmetric tensor product of 2 spin 1 particles. Sort of, that's 1 spin 2 particle. So this is symmetric. But even symmetric, you can get spin 0 and spin 2. So it should also be traceless. Okay? And if you try to put all of this into a relativistic tensor, then you also need H0 anything should vanish. Okay? And you can ask, again, what is a covariant equation, say some 2-derivative covariant equation, which reduces to these statements in the rest frame? And you can go Google this equation if you want, but basically it's the Pauli-Fierz. This is the unique equation, relativistic equation, which then reduces to this in the rest frame. Okay, great. So then again, we can take the m goes to 0 limit of the Pauli-Fierz equation, and where does it lead us? With the suitable non-abelianization, blah, blah, blah. Basically the same sort of roadmap as with the gauge fields, yeah.
Is there some underlying reason why there is one unique equation for both the spin 1 and spin 2 case to satisfy these requirements?
I don't have any way other than having, doing it to see that it's that tight. That a theme that we find a lot in relativity and quantum mechanics is relativity seems to have, it's a tight grammar, but allows a lot of options. Quantum mechanics by itself is a tight grammar, but allows a lot of options. The intersection of the two is like chess. The game is very, very tight. It's like chess in that there are a lot of games you can play, but it's a very tight game, and I don't know why. It's magic. It's more an anthropic answer. Like if it weren't like that, then I wouldn't be in this field lecturing to you. You see, so this leads to Einstein's equations. For this kind of apparently, in this way of deriving it, artificial construct where you define this to be Minkowski space metric plus this H mu nu field. And then this becomes the gauge field, if you want, of general coordinate invariance. Okay, the dynamical metric of space-time. And in this kind of emergent way, this sort of Weinberg-Feynman-like way of thinking about it. And the right-hand side, the source term, in the analog of Maxwell's equation where I put a current on the right-hand side, the source term. Now, because it's a tensor field, the source term is a tensor, T mu nu, okay? And it's also conserved. Okay? And we can ask from this rederiving, who is this source? There it was sort of, if you work it out, that is sort of the electric charge or the current associated with the electric current. Who could this be? Who is this charge that's associated with it? Well, there is something. There's a conserved that implies that there's some conserved charge that you make out of the charge density. Okay. And who is that? Okay. And the answer is, it's now a 4-vector. It's a conserved 4-vector. And in a interacting theory, there is only one possible conserved 4-vector. That is the integral of some local density. There's only one such thing, and that it must be 4 momentum. Now, who says that there's only one? So that's sort of essentially the content of the Coleman-Manjula theorem. But I'm going to give you one exercise just with 2-to-2 scattering so that you can see, you can taste why that's the case. Why couldn't I have, who told me? I know that Einstein said, yes, it's energy and momentum. But in this way of coming at it, who told me that this charge or this current is associated with energy and momentum rather than some other exotic 4-vector charge? And the reason is that there can't be. Consistent with interactions, you can't have multiple conserved 4-vector charges. Okay? So I want to give in the exercises a quick taste of that. So therefore, we see that spin 2 must be a kind of gauge theory of whose gauge charges are energy and momentum. In other words, you're gauging translations, which is what general coordinate invariance is all about. Okay? So now we can go to higher spins than that. How about spin greater than 2? Where I'll speak even more quickly. Okay. That, in fact, m going to 0 is impossible. That when you try to play the same game, it's impossible. Because, again, it would require conserved. So here there was a conserved vector charge. Here it would require conserved tensor charges. Q mu nu, however big the spin is. And these are simply impossible in an interacting theory. And again, I'll give you an exercise to just show yourself that. I don't know who is first, but let's start with somebody new.
We skipped spin 3 over 2.
Sorry?
We skipped spin 3 over 2.
Excellent. I'm coming to that. I did that for a reason.
Is it possible to conceptualize spin greater than 2 for 3 plus 1 dimensional space-time, or do you have to go to higher dimensions?
In higher dimensions, but also in 3 plus 1 dimensions, if you try to write a theory of spin, you find that it can't interact. That's the only problem. You can conceptualize it, but you find, again, that the tight game you're playing says, just from relativity, that it can't interact.
Can it interact in higher dimensions?
I don't think so. I think it's the same game. I think maybe in lower dimensions, possibly like 2 or something. But
Are these only for bosons?
no, these are for. So we're going to do an interesting case because it's going to have a spinner, a fermionic side to it. That's the case that I omitted, right? Spin 3 halves. But even and you could attempt to do it here, like for spin 5 halves. The same conclusion is there. It's just that I wouldn't be able to write it as a Lorentz tensor. I would have some spinner indices, but the same conclusion would be there. Well, let me go here and then.
You mentioned that we seem to have a lot of spin 1 half, spin 1, but for spin 2, there seems to be only one graviton.
Yeah, so you see the reason for the oneness, like you might say, I've been advertising, look, spin 0, nature is so stingy, right? That's basically trying to sneak in the hierarchy problem, even though all of you have been warned that careers end in that direction. But unless you've already got tenure, in which case you're up here lecturing. But so you might say, and the way I've advertised it, look, there's lots of spin half that are massless or approximately massless. There's lots of spin 1. But when I came to spin 2, there's only one that we know of, the graviton. But notice there could only be one, because there can only be, because of the uniqueness of this charge. We can't have multiple charges. It's not like gauge bosons. We have multiple gauge groups and so on. There's only one thing to gauge. Okay, so that's the oneness of it, and how beautifully the universe has given us that one. And it's even allowed us to see it. I'm literally here. There was another question somewhere, yeah.
So this mass almost zero, mass equals zero game, I mean, of course, if you have mass, you can have spin higher than 2. So what exactly is the statement?
Yeah, so that indeed, so let me finish, therefore. Maybe tell me if this clarifies the answer to your question. So, so you can't take, it turns out as you try to formally take this limit, you can't. So, so what would you expect in a world where this is the math, okay? You'd expect that somehow the masses could be, you can't take them to zero. That is, if they're elementary particles, meaning they're lighter than the Planck scale, they can't be much lighter than the Planck scale, okay? They must live somewhere up there. Then it's allowed. Then you could have these higher spin particles, and the only known, so the only perturbative theory of this sort is string theory. Okay, so string theory, famously, if you think like a particle physicist who cannot see the one-dimensional nature of the particle because they don't have a big enough magnifying glass, is a theory with higher spins. In fact, lots of higher spins, towers of higher spins. And as you probably have heard, sort of typically one imagines them to be living near the Planck scale. And it's a weakly coupled theory. At least there are versions of string theory, which are the original ones discovered, which are perturbative theories. That's their great value. You can work things out. And it is, I think, conjectured, and my guess is rightly so, that it is the only weakly coupled theory with higher spins in this way. I think Nima Arkani Hamed had tried to sort of make that a little more concrete. I don't think literally proved that in the generality I just said it, but I think there's evidence to suggest that's what string theory does. It captures higher spins in a perturbative way. But there's another way to do it, which is not perturbative. Okay, so you could have strongly coupled composites. And we have tons of experimental examples, which are hadrons. There are literally fermionic hadrons with spin 7/2, seen in the lab. There they are, okay? So but the main thing is that the masses are comparable to the compositeness scale, the energies at which you start to see their compositeness scale. So there's no experimental limit in which you're unaware of the compositeness because it's happening at a tiny length scale, and yet the particles look light on the, 1 over that scale. Okay, so so it's really beautiful. Again, nature does everything. We don't know about string theory. Okay, so put that aside. It maybe does that, but in the experimental regime, like nature provides us with all of these beautiful higher spin examples. But these are both unfair, right? I'm doing elementary particle physics. These are composites. They're not elementary. That's the dirty trick. Here, it's string theory. It's an elementary string, but it's not an elementary particle. So you could say that actually, therefore, J equals 2 is the end of particle physics. Okay? 2 and below, it's all good particle physics. Beyond that, it's not particle physics. It's something super exciting, but it's just not particle physics. Okay, so that leaves us with the next lecture, I guess. And that one will be, indeed, the case of spin 3/2, which will lead us into, what is going to take up, in the beautiful equations part. It will lead us to supersymmetry and a good chunk of the technical part of what I want to say. I've got a lot of perspective I'd like to give, but there's some technical part, and I think supersymmetry illustrates BSM in the panoramic sense in a very beautiful way that you can actually leave here with a product in hand. And I can try to realize the goal of trying to show how everything could come out of exponential hierarchies, let's say, by putting supersymmetry together with other ingredients. Okay, so I will stop, I guess, and yeah. So the meat of this will then start next time. Good.
I just wanted to thank you for answering all my questions. I know I ask so many of them.
That's okay.
I think it's.
I mean, they were decent. If they were questions that I think nobody wants to know except you, then I will defer it to the end.
Sure. Of
But
course.
if they are questions that I think that anybody might be thinking but not asking, then I will, as I did, answer.
Yeah. Well, I think it's so fun to think about physics in this way. And,
Yeah.
Yeah. So thank you.
Yeah, I hope it's a break from everything else.
And I'm Ann Catherine, by the way.
Okay, good to meet you. Hey.
Could you explain more on this part? Because I probably thought this is rather logical and think this is probably just a motivation for some of the things we're talking about later, but I just couldn't understand this part. I see that, okay, this is RT invariant, and then we jump to the spinning table. I feel there's a lot of gap here.
Yeah, so it's only that, so if we say that e to the minus 1 over alpha m Planck is the proton mass, right? Then
Alpha is the QCD,
and that's the
Planck
QC,
scale,
yeah,
right?
exactly, at the Planck scale. So it's true that you could get any proton mass by choosing this. You could just solve this equation for alpha using any proton mass, right? However, if you're just sort of thinking the way things come out of the Lagrangian that comes out of just below the Planck scale, right? The effective Lagrangian, then it will contain some alpha at m Planck. And we're saying, a priori, this thing could have been anything between 0 and 1, okay? Or 0 and 4 pi, or whatever you want, right? So let me just call it 0 and 1. And so if, and depending on where I live in this parameter space, the proton mass would have either turned out to be maybe close to the Planck scale or anywhere here. But if I just, but if I throw darts, you see that there is a region, let's say order 1% of the parameter space, even a few percent, in which if you go there, you will end up with this proton mass, which is, however, 10 to the minus 18 of the Planck scale, right? So there is something exponential in, if I throw darts here in a linear way, that is any place is as likely as anything, you will find lots of cases in which the proton is incredibly light, right? So now, the formula says everything. I'm just saying what the formula says here. But the spirit of it is thinking like this, right? That the proton mass is not what comes out of matching to quantum gravity at the Planck scale. A coupling comes out. The proton mass is some far infrared consequence, right? So in an RG sense, the thing that we get by matching is some alpha. It could have been, how do I know what it was? Anything between 0 and 1. But if I want to understand why is it got a large, like, is it a robust thing to feel that you have 10 to the minus 18 mass? Did that require a 10 to the minus 18 coincidence in the fundamental couplings?
Yes.
No, it didn't. It only required
You only require
sort of
okay.
1%.
So this is okay. So small variant of this, like 10 to the order minus
So
1,
small
minus
becomes
2,
very
can
small.
Can lead to minus 18.
Now, I don't want to make that into a principle or anything. I just want to taste it. That this is, of course, what is happening in QCD, right? So we see that. We do see the proton mass. We do see that it is very light compared to the scales that particle physicists think about, right? And we know the mechanism is this. And it seems like that is at least a theme of particle physics. Like we learn this mechanism, and it's got this beautiful aspect that there's a big chunk of parameter space which gives you a very squeezed mass, a very, very light mass, right? But it's good you ask, because there's nothing really that I'm saying that's more than this formula. It's only that you're willing to gamble that something like this could happen again, right? And it's worth tossing around and arguing, because maybe you feel like, no, that like, suppose it was the electron instead, right? And you just said, look, I'm just going to say the electron mass is 10 to the minus 20 of the Planck scale. And I just feel like saying, like in QED, forget electroweak or anything. QED, I'm just going to say that. That's good enough for me. That's it's measured to be. I'm going to put that number in the Lagrangian. And I'm saying something feels different. But at least it makes me feel different, whether I put this in or I just ask for 1% and then suddenly, right? Yeah.